Today we'll do the numericals based on quantum numbers and electronic configuration of elements. If you don't know that what are quantum numbers and what do you mean by or how you represent the electronic configuration of element, then I'll provide you the link in the description box. Please go through those videos and then you can easily understand this video. So without any delay, let's get started. So students, this is our first question. First we will solve the questions based on quantum number. So here is our question. What designation is given to an orbital having? Now what designation is given to an orbital means what name you give to this particular orbital. Now which orbital? Whose n is 2 and l is 1. If we recall the quantum numbers, we have 4 quantum numbers. Principal quantum number, second one is azimuthal quantum number, third one is magnetic quantum number, and fourth one is spin quantum number. Principal quantum number is represented by small n. So here it is small n. Azimuthal quantum number is represented by small l. Here it is. So with the help of the principal quantum number and azimuthal quantum number, we have to give the name of the particular orbital. So designation of an orbital means name of that particular orbital. Designation of an orbital means name of particular orbital. So here in the question, the information which we have is the principal quantum number and the azimuthal quantum number. Principal quantum number is 2. Now again, if we recall the quantum number, and if you don't study the quantum number video, or if you have not seen the quantum number video, then please see the quantum number video. Then only you get to know about the principal quantum number and the azimuthal quantum number. So principal quantum number n equals to 2. If we talk about principal quantum number, the value of n starting from 1, 2, 3 and so on, and they are given the name K, L, M and so on. Means 1 for K, 2 for L and 3 for M and 4 for N and so on. So here it is 2. Now 2 stand for, here the 2 stand for K, and 2 stand for L, means second shell. 2 stand for L. So I write 2 here. I don't write L here, I write 2 here. Because n we have to represent as it is. Whatever the number is given to us, we have to represent as it is the number for the representation of an orbital. We don't have to write the symbol which are used for that particular number. So n equals to 2 means here I have to write 2. Now L, the value of L starting from 0, 1, 2, 3 and so on. And for this it is S, P, D, F, because it represents the shell, subshell. This represents shell, the principal shell, and this represents the subshell. So 2 I'll write as it is, but in place of 1 I'll write what? P. So the name of the orbital becomes 2P. So if this type of question is given to us, we have to write the number of n as it is. Whatever number is given to us in the question, we have to write that number. 2 means 2, 3 means 3, 5 means 5, 4 means 4. And in place of L, I have to write the alphabet which is used for that particular number. Now, if I talk about this, here I have to write 3 and here L equals to 0. Now, if L equals to 0, then it is S. So, the name of the orbital is 3S. Clear? Now, this one, N equals to 5, L equals to 3. So, I have to write 5 here and 3. In place of 3, I don't have to write 3. I have to write the symbol which is used for 3. And for 3, I know that the symbol is F. So, 5F. Now, this is your homework. This one is your homework. So 2P, 3S, 5F. If the question is like this, you have to solve the question like this. Now we'll do the next question. This is our second question. Which of the following orbitals are not possible? in this question, the name of the orbitals are already given to us, but we have to tell that out of these four orbitals, which of the orbitals are possible and which of the orbitals are not possible. Now, how we get to know? We get to know this by knowing the concept of the quantum numbers. So, for this question, the concept of the question quantum number should be clear to you. Now, first is 1p. First is 1p. So, in this, I'll talk about the principal quantum number first. Now, here, the principal quantum number is represented by this value. In earlier question also, we get to know this, that the number of that particular orbit represent the principal quantum number. The number of any particular orbit represent the principal quantum number, whereas the alpha bit represent the azimuthal quantum number. So 1 is the principal quantum number, means for this particular orbital, the value of n is 1. For this particular orbital, the value of n is 1. And in quantum number, we studied that if the value of n is 1, then the value of n varies from 0 to n minus 1. It means for first shell, the value of L varies from 0 to 1 minus 1. That is also equals to 0. It means L has only one value and that is equals to 0. For n equals to 1, we have 1. We have first shell. And for first shell, the value of L varies from 0 to n minus 1, where n equals to 1. So 1 minus 1 is also 0. So it means we have only one value for L, that is 0. And the symbol of 0 is S. It means we have only one possible orbital in first shell, and that is 1s. 1p is not possible. It means this orbital is not possible. This orbital is not possible. Now, second one, that is 2s. If I talk about 2s, for 2, n equals to 2. For 2, n equals to 2. And if n equals to 2, the value of L varies from 0 to 2 minus 1. That is 0 and 1. Now 0 stands for S. It means 2s is possible. And 1 stands for p. It means 2p is also possible. So for second shell, two orbitals are possible, 2s and 2p. And here we have 2s orbital. It means this orbital is possible. This orbital is not possible. This orbital is possible. Now we move to third one, that is 3f. Now if I talk about 3f, means n equals to 3. So the value of L varies from 0, 1, 2. Because n minus 1 becomes 2. So 0 to 2 means 0, 1 and 2. So 0 stand for S, 1 stand for P and 2 stand for D. It means three possible orbitals are 3s, 3p and 3d. But 3f is not possible because here the value only ends up to 2. So 3f is not possible. If I talk about 4d, here 4d, n equals to 4. So L equals to 0, 1, 2 and 3. 0, 1, 2 and 3. So the possible orbitals are 4s, 4p, 4d and 4f. It means 4d is possible. So our answer is 1p and 3f are not possible. Are not possible. So with the help of the principal quantum number, we can easily calculate the azimuthal quantum number, and with the help of these two numbers, we can easily predict that whether the given orbital is possible or is not possible. So this is the second type of the question which is based on quantum numbers. Now we'll do the third one. This is our third type of question. How many electrons in an atom have the following quantum numbers? How many electrons in an atom have the following quantum numbers? Means in an atom there are how many number of electrons which have this set of quantum numbers. First of all, in first question, n is given to us, that is principal quantum number, means shell. And if we talk about shell, we correlate the shell with the orbits. And in the orbit, we know that the number of electrons which are present in one orbit can be calculated by using the formula 2n square. Means in any orbit, the number of electrons can be easily calculated by using the formula 2n square. 2n square. So, and ms equals to minus half means spin is anti-clockwise. We know that in Pauli exclusion principle, we studied that in a particular orbital, we have two electrons and both the electrons have opposite spin. Means if we have 6 electrons in the orbit in a particular subshell, we have 3 clockwise rotation and 3 anti-clockwise rotation. So in first question, total number of electrons, if I talk about the total number of electrons in third shell. Why third shell? Because here n equals to 3 and the value of L is not given to us, so it may be 3s, 3p, 3d. Maybe 3s, 3p or 3d. So n equals to 3 means shell is third one, and the total number of electron in third shell can be calculated by using 2n square, means 2 into 3 square. So 3 3 is 9 and 9 2 is 18. So the total number of electron in third shell are 18. But out of these 18 electrons, 9 have clockwise spin, whereas 9 have anti-clockwise spin, and we have to tell about the electrons whose have anti-clockwise spin. So anti-clockwise spin is equals to 6 electron. Anti-clockwise spin is equals to 6 electron. So how many electrons in an anti-clockwise spin electron becomes 9? Half of 18, that is 9. So the how many electrons in an atom have the following quantum numbers? Means if in an atom n equals to 3 and ms equals to minus half, we have 9 such atoms in whose principal quantum number value is 3 and they show the anti-clockwise rotation. So for first, the answer is 9. Now if we talk about second, in second, L is given to us, that is n is given to us, that is 3. In first one also n is given to us, that is 3. But we'll not use this formula in second case. Why we'll not use the second formula in this formula in second case? Because in this, the value of L is also given to us. It means subshell is also given to us. Specific subshell is also given to us. So first of all, we'll write the name of that particular orbital. So 3. In first question, just like first question, the name of this orbital becomes 3s. Why it is 3s? Because 3 represents the principal quantum number and s represents the azimuthal quantum number. So here the orbital is fixed. In first question, the orbital is not fixed. Only shell is there. Means we have third shell and we have to tell that how many electrons in the third shell have anti-clockwise spin. So it is 9. But here the specific orbital is given to us, that is it is 3s orbital, and in 3s orbital how many electrons are there? How many electrons are there? But it is not given that the electron should have positive spin or negative spin. It means we have to tell that how many electrons are present in 3s orbital, and in orbital we know that maximum 2 electrons can accommodate. Therefore the answer becomes 2 electrons. Clear? In this question, why we have applied this formula? Because the orbital is not specified to us. We have only the information about the shell, not about the subshell, not about the orbital. But in this, we have given the specific orbital, that we have 3s orbital and how many electrons are present in the 3s orbital. So here the number of electrons are 9 and in this the number of electrons are 2. So in this way you can solve such type of questions. So this is our next question, which is based on quantum number. Arrange the quantum numbers in increasing order of energies. We have to arrange these quantum numbers in increasing order of energies. Now it is little bit difficult to arrange the quantum numbers, but it is very easy for us to arrange the different orbitals by using the Abhav principle. So first of all, we'll write the name of the orbitals on the basis of the quantum number, which we have already discussed in question number 1. Now first, n equals to 4, L equals to 2. So for 4, we have to write only 4 and L. L equals to 2 and 2 stand for D. So it becomes D. But here we have one more additional information, that is ML. ML equals to minus 2. Now if you have seen my previous videos, you know that if ML equals to minus 2, the D orbital is either xy or x square minus y square. So I'll write here xy. If you write x square minus y square, then also it is correct, because we don't know that out of dxy and dx square minus y square, which one is minus 2 and which one is plus 2. So ml equals to minus 2. Now this is our first orbital. Now second, n equals to 3, because ms represent only the spinning of the electron, that is the electron is moving anti-clockwise here. N equals to 3, so it is 3. L equals to 2, so again it is D. ML equals to minus 1, and minus 1 stand for either D xz or D yz. So whether you will write here xz or yz, both are correct. Next one is n equals to 4, so here it is 4. In L equals to 1, so it is 4p. And we know that ml equals to 0 for pz, so it is 4pz. Now next one is n equals to 3, and L equals to 2. L equals to 2 means D. ml equals to minus 2, so ml equals to minus 2, again I'll write here xy. If I'll write here xy and I write here x square minus y square, then it is wrong, because for minus 2 I am considering that it is dxy. So here also it is minus 2, so I have to write only xy. N equals to 3, so it is 3. L equals to 1, so it is p. L equals to 1, so it is p, and ml equals to minus 1. Now out of px and py, anyone have value minus 1, so I'll write here px. So these are the name of the orbitals: 4d, 3d, xz, 4pz, 3d, xy. Now to make it more simple, we'll remove this xy, xz, pz, xy, px, because we know that if we talk about in the ground state, the energy of the degenerate orbital remains same. So if we talk about dxy or dyz or dzx, the energy remains same. So we can simply write it as 4d, it is 3d, it is 4p, it is 3d, and this one is 3p. Now here we'll apply the Abhav rule, that is n plus L rule. Now we'll calculate the n plus L value for different orbitals. For these orbitals we'll calculate n plus L value. For 4d, n equals to 4 and L equals to 2. So for first, the value of n plus L is, for 4d, the value of n plus L is 6. For second, the value of n plus L is 5, because n is 3 and L is 2. For third, the value of n plus L is again 5. It is again 5. For fourth, the value of n plus L is again 5. This is again 5. 3 plus 2, that is 5. Now for fifth, the value of n plus L is 4. So these are the values of n plus L for these orbitals. Now on the basis of n plus L value, we'll arrange these orbitals, because we know that according to n plus L rule, if orbitals are arranged in the increasing order of their energy, and the energy having higher n plus L value will have higher energy, and the orbital having lower n plus L value have low energy. out of these orbitals, this one is the lowest number, that is 4. So the orbital belonging to the 4 number has lowest energy, because we have to arrange increasing order, means low to high. So first the lowest energy is of 5th orbital, and 5th orbital is 3p. So 3p has the minimum energy. Now above it we have 3 orbitals having the same value, that is 5. Now we also studied in n plus l rule that if we have same n plus l value for 2 orbitals or for 3 orbitals, then the orbital having lower n plus l value will have lower energy, a lower n value will have lower energy, and the orbital having higher n value will have higher energy. Now if we talk about these 3 orbitals, second one is 3d, for it n is 3, third n is 4, and fourth n is 3. So it means here 3 and 4, it means the number of n is greater in this case. It means this orbital has higher energy as compared to these 2 orbitals. Now if we talk about these 2 orbitals, this is 3d and this one is also 3d. So both have same energy in the ground state. So next we have 3dxy is equals to 3dxz. These two have equal energy. Why these two have equal energy? Because these are degenerate orbitals, and in the ground state degenerate orbitals have equal amount of energy. Now next one is obviously this one, that is 4p, and the last one is having the value 6, that is 4d. So in this way we can arrange the different quantum numbers in increasing order of energy. So it is easy for us when we convert these quantum numbers into orbitals. Now here is the question which is based on electronic configuration. So the question is, give the electronic configuration of the following ions. In our previous video, we have studied that how we'll write the electronic configuration of an element. Now in this question, we'll learn that how we'll write the electronic configuration of an ion. Before writing the electronic configuration of an ion, we have to know that how we write the electronic configuration of an element. Without knowing this, we can't able to write the electronic configuration of an ion. So first is Na positive. So first of all, I'll write initially when we start, we'll write the electronic configuration of that particular element. It is in Na, we know that Na atomic number is 11. So the number of electrons are also 11. So Na equals to 1s2, 2s2, 2p6, 3s1. This is the electronic configuration of sodium element. But we have to write the electronic configuration of sodium ion. It is sodium ion and it is cation. Now I think you all know that whenever we remove electron, then it forms cation. Means cation is formed by losing an electron, and anion is formed by gaining an electron. So here it is cation, means it is formed by losing electron. Now electron will lose from the outermost orbital, and the outermost orbital is 3s. So electron will remove from 3s. And what is the charge in Na positive? It is +1. So how many electron will removed? That are 1. So 1 electron is removed from sodium, as a result of which it acquires 1 positive charge, and that electron will remove from the outermost shell. So if we write the electronic configuration of Na positive, we will remove 1 electron from the outermost orbital, and outermost orbital contain only 1 electron. So the outermost orbital becomes empty. Now our outermost orbital becomes 2p. So this is the electronic configuration of Na positive. Now if we talk about N2 positive. Now we know that the atomic number of nitrogen is 7. We know that the atomic number of nitrogen is 7. So the number of electrons are also 7. So first of all, we'll write the electronic configuration of nitrogen. That is 1s2, 2s2, 2p, 2p3. So 3, 4, 5, 6, 7. So the total number of electron becomes 7. Now it is 2 positive, or you may also write it as 1s2, 2s2, 2px1, 2py1, 2pz1. All three degenerate orbital contains 1 electron, and if I write here 2, here 1, here 0, then it is against Hund's rule of maximum multiplicity. So for nitrogen, our electronic configuration is this, but I have to write the electronic configuration for N2 positive. Now N2 positive, again here it is positive charge. Positive charge means removal of electron. Removal of electron, but how many electrons are removed? 2 electrons. So I have to remove 2 electrons from nitrogen. And if I remove 2 electrons from nitrogen, then my configuration becomes, initially it is 2p3. I have to remove electron from the outermost orbital. I am repeating this line again and again, that we have to remove the electron from the outermost orbital. Here the outermost orbital is 2p, so I have to remove the electron from 2p, and we have to remove 2 electron, and this orbital has 3 electron. Now the number of electron becomes 1 if it becomes N2 positive. So this is the electronic configuration of N2 positive. Now third, Cu2 positive. In our previous video, we have studied about 2 exceptional cases, and these 2 cases are copper and chromium. That while filling the electron, how exception are there in the copper and the chromium. Similarly, while removing the electron also there is exception. While removing the electron there is exception. Now first of all, I write the electronic configuration of copper. Now I know that the atomic number of copper is 29. So the number of electrons are also 29. So when I arrange the number of electron, it becomes 1s2, 2s2, 2p, 6, 10. Still 19 I have to arrange. Then 3s2, 3p, 6. And after 3p, we have studied that we'll first 4s and then 3d. 4s, 2 and 3d, 9. But because of half filled and fully filled stability, one electron will move from here and goes here. Then this we have studied in our previous video. I hope you have seen that video. Copper, the configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6. After 3p, the electron will move in 4s and then will move in 3d. This is when this rule we have applied when we fill the electron in the copper. But while removing the electron from the copper, we'll remove the electron from the 4s, not from the 3d. Clear? While filling the electron, we'll fill the electron first in 4s, then in 3d. But while removing the electron, we'll not remove the electron from 3d first. We'll remove the electron from the outermost orbital, and that outermost orbital is 4s. So we have to remove the electron from 4s first, then we have to remove electron from 3d. This is there in copper and chromium. So it is Cu2 positive. So Cu2 positive means removal of 2 electron. So 1 electron I'll remove from 4s, and then I'll remove 1 electron from 3d. I'll not remove 2 electrons from 3d. 1 electron from 4s and 2 electrons from 3d. So my configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 9. Clear? I'll not remove 2 electrons from 3d. I'll remove 1 electron from 4s because 4s contain only 1 electron, and then I'll remove electron from d. In all the elements where we'll fill electron first in 4s and then in 3d, in all the electrons, while removing the electron, we'll remove the electron from 4s first, and then we'll remove the electron from 3d. Now the fourth one, that is Cr3 positive. This one is your homework. You have to show me the configuration of Cr3 positive. Now this is our next question. Indicate the number of unpaired electrons in phosphorus, silicon, chromium and iron. Means we have to tell that how many unpaired electrons are present in these elements. For telling the number of unpaired electrons, we have, for indicating the number of unpaired electrons, we have to know about the electronic configuration. So first of all, we'll write the electronic configuration of all these four elements, and you also write the electronic configuration of these elements with me. First of all, phosphorus. Now phosphorus, the atomic number is 15. So the number of electrons are also 15. So we'll arrange the 15 electrons like this. 1s2, 2s2, 2p6, 3s2. So the number of electron becomes 12. Now still we have to arrange 3 electrons. So 3p3. Clear? Now second is silicon. Silicon, the atomic number is 14. So the number of electrons are 14. When we arrange these electrons, 1s2, 2s2, 2p6, 3s2, 3p2. Now next one is chromium. Now chromium, 24. Chromium, I think you have studied a lot of times, so you can write the electronic configuration of chromium without my help. 1s2, I am writing here, and I hope you are writing there also. 2p6, 3s2, 3p6, 4s1, 3d5. Why I'll write 4s1 here and why 3d5 here, I hope you all know very well now. And if you don't know, then please watch the video, watch the previous video, which is electronic configuration of element. The link I'll provide in the description box. D is Fe. Now the atomic number of iron is 26. So the number of electrons are also 26. So when we arrange, it becomes 1s2, 2s2, 2p6, 3s2, 3p6. The electron first go in 4s, that is 4s2. So the number of electron becomes 20. Now 6 electron will move in 3d. So the configuration becomes 3d6. So here we have written the electronic configuration of different elements. Now we'll write the number of unpaired electron present in these elements. Now if we talk about this, S contain 2 electrons. So this one is filled, this one is also filled, this one is also filled, this one is also filled, this one is not filled. And it contains 3 electrons. Now the number of electrons are 3 electrons. So if we apply Hund's rule of maximum multiplicity, 3px1, 3py1 and 3pz1, it means 3 orbitals of p subshell contain 1, 1, 1 electrons. 3 orbitals of p subshell contain 1, 1, 1 electron. When Hund's rule of maximum multiplicity, according to Hund's rule of maximum multiplicity, if we talk about a degenerate orbital, if all the orbitals are not singly filled, till then no pairing is there in the degenerate orbital. When there is no pairing in the degenerate orbital till all the degenerate orbitals are half filled. Clear? So 3 electrons means 3 orbitals. 3 orbitals contain 1, 1 electron. So each orbital is half filled, means each orbital contain only 1 electron. So the number of unpaired electrons are also 1. Unpaired electrons are also 3. Electrons are 3. Because In an orbital, we have two electrons, and when we have two electrons, the electrons are paired. When we have one electron, the electron is unpaired. In this, these orbitals, electrons are fully filled, means electrons are present in their paired form. But in this, the electron is not filled, and these are present in unpaired form, and we have three orbitals, and three orbitals contain only one electron, so the number of unpaired electrons are 3. In silicon, the number of unpaired electrons are 2, because these are fully filled. These are fully filled. I have to look this only. So this is half filled and not half filled. This is partially filled, means we have three orbitals. Out of three orbitals, two orbitals are filled and two orbitals have only one electron. So the number of unpaired electrons are 2. Here the number of unpaired electrons are 2. In chromium, now we have to see these two orbitals. In chromium, we have to see these last two orbitals, because 4s is also singly filled and 3d5 is also not fully filled. Out of except these two, all are fully filled. In this, one orbital is there and one electron is there, and that electron is empty. So 1. In this, 5 orbitals are there and 5 electrons. So according to Hund's rule, each orbital contains one electron. So each electron is unpaired. So the total number of unpaired electrons are 6. In this, 5, and in this, 1. So the total number of unpaired electrons are 6. If we talk about iron, 4s is fully filled. Now we don't have to see the 4s. We'll see 3d. Now if we see 3d, in 3d we have 5 orbitals and we have 6 electrons. So 1, 2, 3, 4, 5. Whenever all the 5 degenerate orbitals get filled, then the pairing start in the first orbital. It means first orbital contain 2 electrons, 3, 4, 5, 6. It means first one is fully filled, whereas the rest 4 are half filled. So the number of unpaired electrons are 4. So in this way, we get to know that the number of unpaired electron in a particular element by using electronic configuration. This is our next question. Draw orbital diagram for atoms with the following electronic configuration. Now we'll learn that how we'll draw the orbital diagram by using the electronic configuration. First of all, 1s2, 2s2 and 2p6. We represent an orbital by a box. Now first is 1s. So 1s means only one orbital, because s contain only one orbital. So we'll represent one box, and one box is 1s. Now we'll represent 2s. 2s is again one simple box, because s contain only one orbital. It is 2s. Now 2p. In 2p, we know that we have 3 orbitals. So simultaneously, I'll draw 3 orbitals. 1s, 2s, and this represent 2p. One is px, another one is py, and the third one is pz. Now I'll arrange the number of electrons. In 1s, I have 2 electrons. One is clockwise and another one is anti-clockwise. Above arrow means clockwise and downward arrow means anti-clockwise. 2s2, clockwise, anti-clockwise. Now 2p5. Now though there is 2p5, but I'll arrange one here, then one here, then one here, and then I'll do the pairing. Clear? Then I'll do the pairing. When I fill all the degenerate orbitals, then only I do the pairing. So 3, now 4 and 5. So the orbital diagram for first one is 1s2, 2s2, 2p5. Similarly, we will draw the orbital diagram for the B and the C1. For orbital diagram for the B and the C1. For B, it is 1s2. So one orbital, one box for 1s, one box for 2s, 3 box for 2p. Now one box for 3s and again 3 box for 3p. Because we have one orbital in s and 3 orbitals in p. Now 1s, 2 electron clockwise, anti-clockwise. Here we'll apply the Pauli exclusion principle that an orbital accommodate only 2 electrons and both the electrons have opposite spin. So same arrow, parallel arrows we can't able to represent. 1s2, 2s2, 2p6. Now all in p we have 6 electrons, so it is fully filled. So I can write 1, 2, 3, 4, 5 and 6. Now 3s2, 3p3. So 1, 2 and 3. Clear? 1, 2, 3. I'll not write it like this because this is against the Hund's rule of maximum multiplicity. So I'll write here. So for the second one, the orbital diagram is this. Now we'll draw the orbital diagram for third case. We'll draw the orbital diagram for third case. Starting from 1s, one box, second box, 2p represent 1s, 2s, 2p. Now 3s contain one box, 3p contain 3 box. These boxes represent the number of orbitals. I am repeating again and again that these boxes represent the orbitals, the number of orbitals. 4s, 1 and 3d. Now here d. For d, the value of ml is -2, -1, 0, +1 and +2. So the number of orbitals are 5. So I'll draw 5 box like this. It represents 3d. Now when I fill the electron, 1s 2, 2s 2, 2p6, 1, 2, 3, 4, 5 and 6. 3s 2, 3p6, 1, 2, 3, 4, 5, 6. 4s 2, 4s 2 and 3d 7. Now again I'll fill one electron in each orbital, then only I do the pairing because these are also degenerate orbitals. 1, 2, 3, 4, 5. And how many orbitals, how many electrons we have to fill? 7 electrons. So these are 5, 6, 7. So the orbital diagram for this C portion is, C atom is this. So in this way, we can draw the orbital diagram for different atoms by using electronic configuration. So students, that's all for today. Do more and more numericals based on quantum numbers and electronic configuration of element. And if you have any query related to the questions of these two topics or any other topic of this chapter, then you can send me a message in the comment box. I'll surely reply your question. I'll see you in my next video with new topics.